ये वाला जब लग जाएगा ना और भी बेस्ट है और निकल वाला गोभी है तो पालक पनीर और गोभी वाला पनीर और गोभी निकलवा हाँ पनीर और गोभी दवा हाँ बोले एक तो नॉट टिपिकल बंगाली अड्डा टिपिकल बंगाली
people. There are some pictures from our town. On the next slide there is some information about 100,000 inhabitants. It's 700 years old. It's close to the capital Prague. A lot of people know the capital Prague. Capital is 100 kilometers from Liberec. It's about 1.5 hours from airport. And interesting thing is a lot of inventors are coming from Czech Republic. For example, car designer Ferdinand Porsche was born in Czech Republic in Liberec. Actually, it's part of Liberec, Bratislavice. He's famous through the world. He's from Czech Republic. About our university is quite young, 70 something over 70 years. We have 7 faculties and 1 special institute, and we have around 7,000 students. When we are a small university, we have to cooperate, and I show you some pictures, some projects which was developed by 3 faculties. Faculty of Mechanical Engineering, it's my Faculty of Mechatronics, and Faculty of Textile. We developed a few years ago small autonomic vehicle. Here you can see it, and we are cooperating on it. Our part, mechanical engineers, was construction, design, mechatronics, create controlling software, logic, and textile engineers create the cover of this car. On this video is without cover. But we thinking about which part we can improve, and one of the part we can improve is was battery or battery box. This vehicle has standard commercial battery, but we thinking about improvement of battery. Usually batteries use these cells. It's possible some other kinds of batteries, but usually we use cylindrical cells, and key parameter of battery is temperature. Optimal temperature is about 15 to 35 degrees of Celsius, but more interesting is difference between individual cells. Because during the charging, if the cell's difference temperature is over 5 degrees, can be a little bit problem. If it's over 10 degrees, the lifetime of battery going down rapidly. Then we thinking about box for battery which can provide heating, cooling, and other properties. Heating is important. Maybe not for India. For India is better cooling, but in Czech Republic last week we have minus 10 degrees. In the north part of Europe it's possible minus 30 degrees. Before you go by electric car, it's good to preheat the battery for its long lifetime. That we think about the design of battery box, and we start with these layers of batteries. Outside cover, inside cover for we can say mechanical durability, cooling system, heating system, and we try thinking about combine these functions to one layer. Then you can see, and we thinking about composite with heating properties, also maybe insulating properties, and so on. We create few types of composites, or group which was involved in composite part. They create few types of composites, and input for this composite was plain wave carbon, non-woven, copper-coated fabric, melanin foam, and they use graphite particles. And I show you the combination. We create 8 combinations of these materials. First one, only 2 layers of carbon. Second one was the 2 layers of carbon and middle layer with copper. Third one was 2 carbons layer and melanin foam. Melanin foam was there for insulation, and the final one was all the set 5 layer carbon, copper, textile, melanin, and again copper and carbon. And second group was with the graphite particles mixed with the matrix to epoxy resin. This one with standard epoxy resin, this one with some graphite particles. We use handmade procedure for create these samples of composites. That means like this, dry and hot pressing by hand. And on this picture you can see some micro picture or from microscopy. There is the carbon surface. This is layer of carbon, and under that you can see the copper. Here is with the graphite particles, melanin foam, and this is microscopy of the copper non-woven fibers. It's a commercial product we buy. And one of the first tests was about heating, and goal was connect two electrodes to the composites at the electric current and observing what happened. And quite trouble was connect the electrodes to the composites because of resin is not simple to connect properly conductive, but after a few attempts the colleagues was succeed. They use some conductive painting and so on. It was quite difficult, but after few attempts they are able to connect the electricity and produce heat. You can see here the graph of heating of composite. This is the two layer of carbon and voltage 2.5, 5 and 7.5 volts, and it's possible to heat it by 2 minutes to up to 60 degrees, and after that was stop the current and we observe cooling of this slab. I have to be faster. Of course, we done a lot of mechanical tests. You can see here DMA results. Also, electric field shielding can be also important thing for batteries, and also other group which I was involved in make a lot of simulations, and procedure is shown here. And final product, it was for testing, look like this. There is a plastic cover, is PVC foil for protection from rain or something like this. Middle layer is here. It's from PA6. First attempt was made by 3D printing. After that we reinforce it with carbon filaments. We have a robotic placement head for thermoplastic carbon filaments, and here you can see the animation of some simulations of falling of battery, and here is final information about cooling system, because typical cooling system is made by not hoses but metal hoses, and it's difficult assembly the hose between or among the all cells. We use the hyperelastic hose. It's very simple to assemble the battery, and we create a sample for testing, apply the thermocouples, and colleague tested charging of battery and difference between individual cells. For cooling we use only air, and from this graph it's not so clear, but this top graph is without cooling, and temperature difference about 7 degrees is not good for battery. But if you use only pressure 1 bar of air, the difference decrease to 3.5 degrees of Celsius, and it's very promising results. And on this picture are our colleagues working on some software for battery. You can see here the heating layer, the battery, and some applications he's creating. We finished this small battery and working further for bigger battery, and maybe in some future we create battery for all passenger cars. It was quite quick because it's not time for all the presentation. Thank you for your attention.
If you want to discuss something, it's time for discussion. And if you have any questions.
Environmental phase or environment?
Environment.
Yeah. Because nowadays plastic is a very big issue.
Yeah, plastic is issue. Actually, at our university we tested for biodegradable plastic, and it's maybe way. Of course, we are working also on nature fibers composites and other kind of composites, but it's not nature friendly right now, but in future I hope it will be fully recyclable. But now it can be a little bit problem. You are
Thank you.
right.
Thank you.
Okay, thank you so much for a nice talk. So let's move to next presentation. Our next, and the title of his talk is 3D structural composites for multi-mode loading.
Good morning, everyone. I hope I'm loud and clear to the end, although there are not too many people here. But it's wonderful to be here at TIT, and I would like to take a second to express my heartiest gratitude to Professor B.K. Behera, the director of this institute, and also extend the heartiest gratitude to Ministry of Textiles, the PhD, CCI, Chamber of Commerce, and of course all the organizers, professors here in the college, and all the students. So today, this morning, when Professor Behera gave his lecture, who was my doctoral father, and I got my PhD under his supervision in the year 2024, he already explained some part of it, but I will go a little bit detailed. And I hope there are some bachelor's, master's, and PhD students here who would be interested to know how the research should be developed in the form of idea, how the methodology should be constructed, and finally how to do the characterizations and go deep into it so that you can tell a story about it. Research is nothing but a scientific story. So just to let you know that I'm representing two institutes, because I did PhD from IIT Delhi, and some of the work that I have done I will be showing today, it's from IIT Delhi. And now I'm working in Hochschule Niederrhein, University of Applied Science, in Mönchengladbach and Krefeld, located in Germany. It's particularly quite popular for textile engineering. In this presentation, I will talk about where we are living, why the impact behavior of fiber-reinforced composites are quite important, the motivation of 3D weaving, and what is weave architectures in 3D weaving, and what is the low velocity impact behavior of 3D woven fabric reinforced composites. And we will discuss a little bit of results and discussions. So in December 1968, when the crew of Apollo 8 became the first people to leave our home planet and travel to another body in space. So the crew was Frank Borman, James Lovell, and William Anders. All later recalled their most important thing, which they discovered while they was traveling outside the space, and that was discovering the Earth. And how they discovered it, that was designed through a lunar reconnaissance orbiter LRO system and try to imitate the image. And after that, so many times, so many rockets and people, astronauts, they traveled in the outer space and looked at our world, and they found that we are living actually in similar world, although in so many cases the European people might think that they are living in a different world, Asian people think that they are living in a different world, but that's not true. We are totally interlaced, interconnected in this neural networking system. So if it is a problem for me in Asia, it is also a problem for Europe, and probably yesterday you saw the news that how the war began between US and Iran. So yes, it's a problem, and we need to tackle it. So the university where I work, we try to combat the whole thing between the sufficiency, consistency, and efficiency. And we are trying to create the future through our weaving. How? We are trying to weave the technology, material, process, management, policies, and all kinds of deals so that we can be connected through the digitalized platform, which became very, very important for us. So now let's talk about a little bit fiber reinforced composites. As you know that it has been in the scenario for the last 50, 60 years, and they've been heavily used in aerospace, and you can see from this picture that over the years, the usage of fiber reinforced composites have superly skyrocketed in Boeing and Airbus manufacturing. Today, this morning, Professor Sabas mentioned in his lecture about it, and this is a graph that you can see that how much advancement so far happened, especially the fiber reinforced composites in aerospace structures development. And in automotive sector as well. There are so many parts in automotive sector, they are also developed through these fiber reinforced composites. If you look at the picture very carefully, you will see in automotive sectors, the usage of composite materials are more than the homogeneous materials like steel, aluminum, and others, to some extent. And as Professor Behra also mentioned in his lecture, that how this usage and the market is growing towards a direction, it's going to be a $71 billion US market by 2031, with a compound annual growth rate almost 10.75%. And they will be involving in electric vehicle, they will be involving in aerospace, in automobiles, in hydrogen vessel, which became a very important topic for using hydrogen fuel as a component for automotive industry. I would like to take a moment for my Indian fellows. So this is the example that Goddess Durga, and I would be very happy to let you know, we manufactured Goddess Durga through fiber reinforced composites. So first it was constructed through this conventional hay, give a structure, then the mud, and then they converted into fiber reinforced composites, and finally the product is something like that. And I'm very proud to tell you that in Mönchengladbach, where I live, we celebrated in October 2025 the first time the Durga Puja festival for 4 days consecutively. 800 people came, and these sculptures will be stayed with us for more than 50 years. And I hope, as it has been protected in the right way, the boxes you can see, they will not be changed in color. So that's also a part that how mythology belief can be converted, the science converted into the societal benefits as well. So maybe the people who are from Calcutta, we will not throw our goddess in the river after we finish our worship. We can keep it together if we make it through fiber reinforced composites. So now let's talk about what is impact. Obviously, impact is a high force or shock that is applied over a short period of time, and our two bodies are collided. It's a very typical, straightforward kinetic energy that formula that we know. And if we think like how we would like to evaluate the different impact events based on the velocity of the impactor, we can say low velocity, which is below 10 meters per second of the projectile. The high velocity, a little bit greater than 11 meters per second. The ballistic is more like 500 meters per second. And hypervelocity, which is like supersonic, like Concorde aircraft was like 2,000 meters per second. So why it is important to study, especially in the critical engineering application? The main reason is because as we are using more and more fiber reinforced composites, we have to understand that they are taking a major part of the share in the structural body of the aircraft. And they are very prone to different types of impact events, knowing or unknowingly. So 90 out of 688 repairs, which happened in Boeing 747, where the average life was 29,500 hours, these all happened. Most of the incidents were by low velocity. As airlines is one of the heavily regulated plays, obviously we need to think about the safety of that. Otherwise, none of the product which we will be trying to use in aircraft industry will not pass the FFA regulations. So when we are talking about lightweight engineering structures by textile reinforcement, we have to think that how we would like to design it. Previously, the chances were very limited where the unidirectional materials or 2D biaxial with stacking sequence 090, 045 and all others. We designed it, but there was a major issue. And the issue were, they were delaminating, the buckle who were interlaminate crack was happening. So there was a disconnect between the layers and it could not be satisfied as an integrated structure. For that reason, we had to introduce 3D weaving technology to get a near net shape structures. The reason is, if it's a near net shape structures like honeycomb, which you probably saw during Professor Behra's lecture, they can absorb enormous amount of energy under impact load. And for that reason, we need to re-engineer, redesign the preform, the very basic part. And then we need to think about which matrix part we will be used to incorporate and satisfy the requirement of mechanical attributes that we are looking for. So for that part, the conventional FRC, where there is a disconnect between the laminates and layers, besides this 3D oven, you can see that they have a true thickness, the red color, true thickness reinforcement there. Sorry, something happened. I need some help. I was here. So what I was saying, like this true thickness direction, it allows us the homogeneous manufacturing possibility of preform. And what's the benefit of it? So the interlaminar will not be disrupted, will not be divided, because the true thickness structures will arrest the crack propagation or any kind of impact event which may occur by the external projectile. So the motivation of this 3D weaving is we can create a near net shape structure. A near net shape means it can be T-shape, pie shape, it can be contour shape, it can be a shell shape. And the reason is because if you look at the structures, the critical point of these structures is actually this junction point. And if it was stacked or adhesively joined, it could be separated. But if it is interlaced in a non-crimped manner by 3D weaving technology, the chances of getting disrupted by the external force in this weakest point area would not be a matter, because they'll have better resiliency against this impact load. And that's the reason the 3D weaving plays a role here. Potentially 3D weaving can be used in a different forms, in all kinds of hollow structures, solid structures, all kinds of contour structures, even in the nodal structures form. And the benefits of this, you can get a near net shape without any welding or joining in a very critical area where impact load can cause a very disruptive fatal incident. So for this research, with the results which I will be showing here, I did it through this mechanism. First, we did the cross-sectional analysis, and then through a software, we tried to understand that how the binder path with the yarn will be pathway. And then we used a multi-layer 3D weaving machine, which are made in India under the leadership of Professor Behra. The machine came to our lab in 2020. By the way, it's actually made in Haryana, the company called Dashmesh. They gave us the loop and we tried to make 3D woven structures. In this research, I will mention that the weave topology, our weave architectures, can be explained in a different way. One of the ways is use a different type of conventional weave designs that we know, like basket, plane, twill, angle interlock. And another is, what is the impact if we change the velocity of the impactor or change the impact energy threshold? So if you look, I took 6 different structures here. 3 of them here which are like very conventional plane structures where the laceover point is quite high. When we change the binder pathway, this is orthogonal twill, there is a basket structures with a shorter float. That's why I gave the name called mat 1 up, 1 down. When I increase the length of the binderian pathway, mat 3 up, 3 down, and then again we change the perpendicular direction of the Z reinforcement on the plane in a very little bit angle way. We call it angle interlock, that's why, conventional angle interlock plane, and then angle interlock twill. And we manufactured 100% E-glass, used 600 Tex reinforcement, and we developed these 3D oven structures. So these are the specifications. We try to keep the gram per square meter, the areal density of these structures, very close to each other, so that there is no manipulation in fiber volume fraction. But of course, due to the nature of the weave architectures and the binder float pathway, the changes of the crossover points, the changes of a little bit of stuffer warp fiber volume fraction, binder warp fiber volume fraction played a significant role, and that's what I want to prove here. So the manufacturing of preform to composite was pretty straightforward by using an industrial VRTM machine, which is also made in India by a company from Gujarat called Indach. And it has a wonderful temperature gradient system as well, because you could do manufacturing with the temperature so that curing happens in a very nice way. I spent quite a bit of years to make these composite structures as good as possible with the homogeneous homogeneous penetration of the matrix with glass filament. So in this case, well, we try to do the out-of-plane impact testing. We try to test 5 different impacts from these 5 different nominal heights and impact velocity, kept the total weight of the drop weight exactly 10.40 kilogram with the same shape of hemispherical 12.7 mm. Maybe you can see an example of when at 50 joule it was used, my structures were fully perforated. For how did I choose this 16 to 50 joule in this segregation? I had to do a series of experiments, nearly 50 samples I had to waste to understand what is the lower threshold, what is the intermediate threshold, and what is the perforation threshold. So before I go deep, this is for the students actually, not for the senior researchers, that how you should understand the data which you are receiving. What your data is saying to you? Is it telling you a story? If you look at it very carefully, it's telling you a lot of stories. This is one example. Same structures, orthogonal plane, 1 up, 1 down, under 60 joules. The behavior of force time and behavior. Should I have? Please give me a grace, a couple of minutes. 3 minutes. Give me 5 minutes at least. Right. So, and if you see the gradients there, you will understand that the behavior at 60 joule of these structures, where's the Hardian failure come at the very late force when it was deployed, but in the Hardian failure at 50 joule it happened quite early. And for force displacement curve, we can decide that what was the nature of the structure under this 16 joule and 50 joule. It was not perforated at all, so rebound happened, and it was absolutely perforated with a lot of friction after the peak force. This is the peak force with the structure. As time is short, I will go a little bit quick now. So let's say another way of how to evaluate force displacement curve for more data that you are looking for. Because this is not a straightforward curve, it's telling you a lot of story. What is the initiation energy you are getting before the peak force has been achieved under the impact event? What is the perforation energy area you are receiving after the peak force? The reason is In this force displacement curve, as I mentioned, in 60 joule, I got rebound for all structures, 24 joule, rebound and onset perforation, which is intermediate one, 32 joules, some structures, onset perforation and perforation happen for some structures. And obviously, 40 joule and 50 joule give me the complete perforation. But the interesting fact is, it's telling me that how can I make a relationship among them, give a ranking. And the ranking I would have given by the calculating bending stiffness from this force displacement curve. And I found that orthogonal Mach 3 up 3 down structures, which is way non-conventional we've designed for 3D open preform, give me the highest value of material factor. Which means it's a better structure, so we don't use it in a regular conventional. We always use the plane or two-wheel or something, not the mat. And then I try to do the energy profile diagram, try to understand the structures, how they behave over the period from 16 joule to 50 joule. Are they giving concave polynomial regression or convex polynomial regression? Because I wanted to see that how they are telling me the story. So the story was quite clear to me. When you change the binder pathway, it changes the behavior. And of course, it depends that how you are implementing it for analyzing the view. And of course, for example, this Mach 3 up 3 down, which I'm very profound about it, it's going in very, very positive direction with absorbing more energy upon the impact energy applied to the event. And finally, I try to calculate the ductility index by evaluating the area of initiation energy and the perforation energy. And for me, the structures which can retain intact in initiation energy area, it's the good one. Because the structure can sustain longer before it goes to the peak force. And then we did the X-ray testing, and we tried to understand the perforation and the damage area of it. And it's telling me an incredible story. The structures with the basket form did not catastrophically propagated the crack. It stopped the crack in so many ways. You see, it's a very small crack you can see. But for other structures, quite big hole or puncture happened. And also, when we try to evaluate that fiber volume, the area and how the matrix was penetrated, I found the same thing. The Mach 3 up 3 down has lower interior and crossover points, and it was homogeneously impregnated with the matrix. So I did also this relationship with in-plane, this IJO testing, and try to understand this interior and crossover points relationship with the drop weight impact and IJO relationship, and I found one thing very interesting. If you have less interlace points in your open preform, your drop weight impact behavior increases more, but in that, it's the opposite in in-plane or edgewise ISO direction, because if you have more interior and crossover points in in-plane impact, their behavior changes totally. That's why my Mach 3 up 3 down structures, you see, they are good at in this drop weight absorption, impact energy absorption, but not good at in in-plane impact energy absorption. I did also this CAI, compression after impact, and I found quite an interesting story, which I can tell from the images here rather than the graph, that none of the load, even after the puncture, it was not damaged in the direction of where my impact happened. It means the true thickness reinforcement did not let the compressive force to come down to my punctured area. Okay, I'm finishing it just to let you know, for the young researchers, we need to think about that how we should do our research data management system. And in our university right now, the project which I'm working called Smart Interface, we are trying to develop a methodology so that data doesn't go with you with your computer or after you leave the university. It should remain in the university system so that next generation researchers can access it and talk with it the way you talk with your ChatGPT. And this is the way we are trying to do it through this circular loop method that is called Visions tool. We created a domain and a research environment where people can collaterally put a lot of information there, and the next generation researchers can talk with that. I I would like to finish this presentation and would like to thank everyone. You can catch up with me. This is my contact information. You can take a picture of it. You can reach out to me. I would be happy to satisfy any of your questions that you have. Thank you so much.
I have a query.
Working as an advisor to the textiles industry in Panipat. So the research which you have shown and you have mentioned that the technologies, the weaving capacities are available through some vendors. So what kind of, I'm talking about the application, that what kind of high-tech final textiles could be made out of it, and who are the technology providers so that the TRL level, technology readiness level is at advanced state, and some investors can come and invest and set up industry out of it, out of your research.
So 3D weaving preform and their composite they are using in aerospace industry for the structural body part, automobile industry for door panels, rooftops, okay? Also for submarines, if you think about, or marine structures, even in wind turbine blades. So all of these, what I have shown to you, for example, like conventional wind turbine blades, you know, they are made, lay up a randomly oriented glass pipe. But it's quite heavy when you lay up a lot. But if we change it through the 3D weaving technology and create a structure all through hollow in a wind turbine blade shape, that would be much easier to transport, or even in the 300 feet above. Or the airfoil structures for the wing panels for the aerospace, they can be also re-engineered with this near net shape, which I just showed through 3D weaving technology. So they are the beneficiaries we will get. And for industry people, it's a leap of faith. You have to invest a little bit because the TRL level so far for all these are now at the level of 4 and 5. But if you want to do it at 7 or 8, the big industries need to put a lot of effort and faith on the engineers like us or the researchers so that we can come up with a cost-optimized product.
Next presentation. Our next presenter is Dr. Comble from Dr. B.R. Ambedkar National Institute of Technology, Punjab. And the title of
Dr. B.R. Ambedkar, NIT Jalandhar. So the title of my presentation is Electromechanical Behavior of Self-Sensing Textile Reinforced Composite. This is the work of my PhD student. So as we know, the composite materials are the combination of 2 or more materials and whose mechanical properties are better than the constituents. So when these composite materials fails, they fail by fiber pull-out, by debonding, matrix cracking, or fiber fracture or buckling, right? But these, for example, the micro cracks or the debonding within the particular composite structure, if it is not identified earlier, the structure fails catastrophically. And therefore, only the concept of structural health monitoring is developed. This structural health monitoring aims at detecting, locating, and quantifying the damage in the composite structure at an early stage to avoid any unexpected failure of the structure. So, there are various types of structural health monitoring systems developed to identify the damage within the composite materials. Resistivity based methods for detecting the damage non-destructively within the composite material is one of the technique. Using this technique, you can detect micro scale damage to the milliscale damage within the composite materials. So the resistivity based method we are using to develop this strain monitoring sensors using the textile materials as a substrate, and this particular strain monitoring sensors uses this piezoresistivity principle. So this piezoresistive sensing sources can be intrinsic type or can be extrinsic type. And the sensing approaches could be self-sensing, or you can use piezoresistive matrix materials, or piezoresistive surface deposited or mounted sensors, or embedding the piezoresistive sensor. And this is one of the important terminology when you are developing this piezoresistive material, that is percolation threshold. So this is the probability at which, or the point at which the connected path first span across the system and transforming it through the disconnected, transforming it from a disconnected to a connected state, and the current flow starts in this particular sensor. Strategies for the selection of the piezoresistive sensing approaches. So it is based on, first is gauge factor. This is very important when you are developing strain monitoring sensors. Gauge factor is simply the ratio of fractional change in the resistance divided by the strain experienced by that particular composite material, based on the manufacturing method and based on the detection capability. So at NIT Jalandhar, we are using glass textile as a substrate and epoxy resin as a matrix material to develop these strain monitoring sensors. The nanomaterials we are using for creating the conductive pathway is the reduced graphene oxide. We are also using titanium dioxide as it is a semiconducting material, and chitosan. So we have developed two methods. One is the matrix-based method, and another is the coating-based method. So this method is our patented method. So this particular method, if you see here, ethanol initially, in case of ethanol is mixed with the nanoparticles, that is reduced graphene oxide, and then epoxy is added into this particular mixture, and you have to continuously stir this particular mixture at 75 degrees centigrade, and then evaporate this particular ethanol and add the curing agent into this particular epoxy resin, and then apply it on the substrate, that is glass textile, and this is how we develop this particular sensor. And this is the coating based method. This is again it is the materials are same, the method used to produce this particular sensor is different. Now these are the, so after developing this particular sensor, we measure the resistance using this particular instrument, right? So initially we have tried to identify the percolation threshold. So this is very important when you are trying to develop strain monitoring sensors, and we have identified this percolation threshold, that is 1% RGO content is the percolation threshold. And you can see these are the microscopic images, optical microscope images of the sensors developed using this matrix based method. So coming to the, we have done a lot of study on this particular sensor. So initially we have studied the effect of length and width of this particular sensors on electrical resistance of the on its electrical resistance. So we have changed the length of this particular sensor and as well as the width of this particular sensor. So when we change the length of the sensor, the electrical resistance definitely increases, right? We know that. And as well as when, but when we are increasing the width of this particular sensor, the electrical resistance of this sensor has reduced. No, electrical resistance has increased. Then, after understanding this, we have developed these particular sensors using different textile structures. For example, unidirectional structure as well as using the bidirectional structure. So these are some of the specimens. So in case of this is the effect of length and width of the glass toe and fabric specimen based sensor on electrical resistance of this particular sensor. So in this from this particular graph you can see that when the length of the sensor is increasing, the electrical resistance is increasing up to some kilo ohm, and after that it becomes almost constant. Further, we have tried to change the geometry of the sensors and put this particular sensor in the composite material. We have understood from this particular experiment that with increasing the length and decreasing the width, the electrical resistance of the sensor shows the decreasing trend, and the sensors produced using the glass toe shows higher electrical resistance as compared to the sensor made from the glass fabric, while keeping all parameters constant. Further, we have studied the effect of sensors length and the stacking position on the electromechanical performance. So stacking position means where you are actually implementing this particular sensor within the composite. For example, at the top or at the middle of the laminate or at the bottom of the laminate. So from this particular experiment, so here from this particular animation you can easily understand that how this particular sensor was implemented in the composite material, and this is the setup to analyze the electromechanical performance under quasi-static 3-point bending test. So with increase in the displacement, the fractional change in the resistance, that is the gauge factor on the y-axis, you can see that. So with increase in the displacement, the gauge factor was found to increase, right? And this FCR, that is fractional change in the resistance for different length of the sensor, is also shown here in this particular picture. Similarly, in this particular graphs, you can see the comparison of FCR with versus the displacement for different length of the sensor for spatial positions, different spatial positions at the bottom, at the middle, as well as at the top. So again, as I said you that previously, that we have developed these particular sensors by changing the geometry of this particular sensor and studied the electromechanical performance of these sensors, and again we have seen that when the displacement, that is the displacement is increasing, there is a increase in the fractional resistance, fractional change in the resistance. So let me go to this particular slide where we have compared the two methods of developing the sensors, that is matrix based method as well as the coating based method, and we have seen that in case of so again here we have checked it with the toe based sensor as well as with the fabric based sensor. So this is particularly for the fabric based sensor. So here you can see that in case of coating based sensor, the gauge factor is comparatively higher compared to the matrix based method. And inferences from this particular study is that sensor made of single 10 mm and 15 mm wide strips are showing less FCR and gauge factor than 2 and 3 5 mm strips in parallel, and gauge factor of composite embedded with RGO TiO2 based sensor is higher than sensor made up of RGO dispersion. Flexural load of composites embedded with sensor at 3 to 12% lower as compared to the parent composite. So further work which we are doing on this particular sensor is trying to calibrate these particular sensors and developing a methodology to calibrate these particular sensors, and trying to implement these particular sensors in various other structures. For example, 3D printed hollow structures as well as 3D oven hollow structures, and trying to understand the electromechanical performance of these particular structures. Right, that's all. Thank you.
We have 3 to 4 minutes. Any questions from audience? Layer, how many layers the graphene? Whether you used a single layer or multi-layer graphene?
It was, are you asking the RGO, whether it is a single layer RGO or multi-layer?
Yes, graphene.
Graphene also, it was a multi-layer.
Okay. Did you functionalize it before using purple perimeter composite?
No, sir. We are not functionalizing. We are directly using as it is and applying on the. We are directly purchasing from the market and applying on the composite. I mean the reinforcement.
So, do you think if the graphene is functionalized with any function group, the performance will increase?
There is a possibility. There is a possibility, but we have to again the critical thing in this particular sensor development is the percolation threshold. So we have to look at that particular percolation threshold. That's why only we are trying to embed, add some titanium dioxide into this particular, because TiO2 is a semiconductor material, and it will not. I mean, when this particular sensor is under, let's say, 3-point bending, so the tunneling resistance. The tunneling resistance is highly depends upon how this RGO is connected to each other within that particular, and when the material is under 3-point bending load or let's say impact load. So if there is a no presence of TiO2, the result or the change in the resistance shown by the composite will be maybe different than what is actually within that particular laminate.
Thank you so much. Thank you. The next presentation. Is Dr. Parshit Paul from Maharaj Ranjit Singh, Punjab Technical University. And title of his presentation is Hybrid 3D Dimensional Composites.
My topic is acoustic behavior of hybrid 3D open fabric and also 3D open composite. So in this slide we have the definition of acoustics, and acoustics is a branch of physics. All this it is mentioned here, and you can see here we have the large wavelength, and then we have diffraction, and there is also the vibration direction and propagation direction. So why is this important? Why we require the study of acoustics? And acoustics is very much a requirement in daily life. Why? Because it creates a pleasant environment, good listening conditions for speakers, musicians and listeners, also living environments and working areas free from harmful noise and vibration. Now, in case of sound, we have two types of sound. We have these direct sound and indirect sound. And in case of direct sound, we can see that direct sound is just direct, and indirect sound is also coming from a reflective surface. And then we have here we have the interaction between sound and environment. Sound, without sound we cannot survive, because sound is a basic medium of communication. But excessive noise can create a deleterious effect on the audience and on human being, and also on the natural habitat. So noise pollution is affecting human as well as it is also affecting the animals, and it is also affecting the insects, everything. So basically we have outdoor noise and indoor noise pollution, and these are the we can see what is the outdoor noise and this is the indoor noise. And then in case of noise pollution, why we require the noise pollution control? Because we require fabricating quiet machine and designing building and structure and using sound absorption material. And then we have these major areas where noise control is essential. We can see that we have residential noise control, then automobile, and then aircraft and space. Basically, aircraft, spacecraft is not affecting us, and during injection of spacecraft it creates noise. And then we also require the building modification. And then we have the methods to reduce the sound energy by acoustic material. Basically, we have this principle like sound absorption, sound dampening, and sound insulation and vibration isolation. Then in case of acoustic absorption, we can see that acoustic absorption manifests into different types of energy like heat, mechanical and deformation. And then a number of sound absorption material exist. They are able to absorb sound wave, depends on the frequency, composition, thickness and method of mounting. So there are basically three primary types of sound absorber: coarse, membranes and resonance. Now, why textile are used for acoustic? In case of conventional material, we can see that we have mineral wool or polyurethane foam, but mineral wool is hazardous hazardous from the aspect of respiratory disease, and polyurethane, in case of polyurethane, we can see that it generates various types of gases. And then in case of textile, we have the advantage of lightweight and porous structure, which is favorable for the sound absorption. In case of textile material, we also have the flexibility in structure. And then natural fiber, fine synthetic fiber, we can various cross section we can use. And then in case of textile, we can have the existing manufacturing technology like weaving, knitting, and also this non-woven. In case of weaving, we have the least production rate, and in case of knitting, we have 10 times production rate, and in case of non-woven, we have multiple times, 100 or 1000 times of production rate. Then we have the limitation of the acoustic structure. In case of limitation of the acoustic structure, you can see we have the low density of textile structure, and then textiles are not isotropic in nature, and then we require the pre-treatment. But in case of the 3D structure, we can using 3D structure we can get a thick structure, because thickness is a requirement of your sound absorption. And then in case of fibrous material, we can see that these are the fibrous materials which we can use. And then we have the limitation of the acoustic textile structure. Already we have said that low density. And then in case of this development of 3D hybrid fabric, we have used this electronic Dobby loop, and these are the specification of the Dobby loop, and then this 3D oven composite is manufactured using this uh, using this vacuum assisted resin inclusion molding. And then we have the characterization of the developed fabric, and then we have the acoustic characterization of the textile material, and we can see that we have to measure the sound absorption coefficient, and then it is also measured at 1/3 octave frequency of 50 to 6300 hertz. Then this is your the actual impedance diagram, effective impedance tube, and then we have the calculation of the noise reduction coefficient. And in case of noise reduction coefficient, we have just taken the average of this sound absorption coefficient at different frequencies, and then we have the calculation of the sound absorption coefficient. And in case of methodology, we have this sample preparation and of 3D orthogonal fabric and development of thermoset composite. And in case of this hybrid fabric, we have different types, up to 11 category of hybrid fabric we have developed. Then these are the diagram of the hybrid fabric, 3D hybrid fabric, and these are also the diagram of the 3D hybrid fabric. Basically, we have taken jute and jute of 982 ticks, and then 491 ticks, and also waste we have taken 1000 ticks, and then also we have taken 600 plus. Now, in our previous study, we have seen that jute is a very effective sound absorbing material, but in case of jute, the jute material deteriorates very easily. So, to impart the strength, we have added glass fiber. Now, in case of this, we can see that these are the specimen, and then we have the mean inertia, and this is the standard mean error of the inertia, and you can see that we have the exemplary acoustic behavior of HY1 and HY2. Because why? Because they are entirely made up of jute fabric, and in case of jute yarn, we have a multi-scale micromorphology characteristics of jute yarn, which is responsible for this better sound absorption or better acoustic behavior. Then here we also have the sound absorption coefficient, and in case of sound absorption coefficient, you can see that the addition of glass roving has caused the reduction in the sound absorption characteristics of HY3 and HY4, because glass is having a solid cross section and due to this solid cross section, there is no void inside the fiber, so it causes the reduction in the sound absorption reduction in the sound absorption coefficient. Then in case of composite development, why we require the composite development? Because we require acoustic insulation. Acoustic insulation is also important, as well as acoustic absorption. In case of this, we can see that we generally use it in building and civil structure, and this composite possesses excellent properties like low weight and high strength, stiffness, impact resistance, and this in conjunction with other sound barrier filler, we can enhance the sound transmission loss, and sound transmission absorption can also be enhanced. So these are the diagram of the 3D hybrid composite which we have manufactured at IIT Delhi, and then then here we have the noise absorption coefficient or noise reduction coefficient, and in case of noise reduction coefficient, we can see that there is no particular behavior exist because all of these, in case of this composite, manufacturing of composite, we have used epoxy resin, and along with epoxy resin we have hardener. Epoxy resin basically made up of hardener and cross-linking agent. So due to hardener and cross-linking agent, they have created a very complex chain-like structure, complex bonding structure inside the material, and so as a result there is a very less option for the acoustic absorption. So as a result all of the material behave erratically, and so we do not find any sound absorption coefficient. Now one thing we have done wrongly, because we shouldn't have studied the acoustic absorption. We should have studied the sound transmission loss behavior. And in case of the thickness of the material, we have used 3 mm. But to have standard acoustic insulation, the material thickness should be higher than should be equal to 5 or more than 5. So, and in case of this, then we have studied the tensile strength, and in case of this tensile strength, we can see that depending upon the constituent fiber, the tensile strength has typical tendencies, like in case of HOA6 and HOA7, you can see that we have the highest tensile strength. So here we have inference, and inference we can see that already I have said that mid sound absorption coefficient of mid epoxy resin is less than the fiber, and composite having different stuffer layer and all this, they are having the same absurd behavior. This is due to the infusion of epoxy resin. Therefore, we have to develop the composite material for acoustic material. Then the selection of reinforcement should be made purely based on end use, and where we have the importance of strength and impact and textural characteristics, it is the main criteria of the reinforcement structure. And when we are going to prepare composite, identical fiber volume fraction should be there, and there is no significant difference in the sound insulation value. Conclusion: the addition of glass roofing has caused a reduction in the sound absorption characteristics of 3D hybrid woven fabrics, and the presence of epoxy resin decreases the sound absorption characteristics of the composite. So that's all. If you have any questions, you can ask me.
Thank you so much. If you have any questions,
overall porosity on sound absorption. You didn't consider any theoretical model?
No. Because we don't have that Nordson. What is it? Nordson.
Several models.
Nordson. We don't have that Nordson.
And in your results that you are showing, how many measurements you perform for each sample? Because if you want to compare between two types of samples, they need to be statistically significant. For that you need to repeat measurements. How many times?
I have studied five samples.
And they were consistently?
Yeah, consistently. In case of composite, we had a problem, that is, actually we have studied acoustic behavior in IIT first time. So when we have cut the composite material, then we should have considered the inside diameter of the impedance tube, and that inside diameter of the impedance tube should be the diameter of the composite. But that's not done. There is some mismatch. So due to this mismatch, also there can be problem. Okay. Any other?
Thank you. Any other question?
What we have said is significant difference is
significance test you have done?
In case of statistics, we have done a standard error. Standard error.
No, significance test.
No, significance test. No, I don't know.
Thank you so much. So we have to move to next presentation. So next presenter is Vikas Katka. From Indian Institute of Technology, Delhi. Pseudo-ductile behavior of glass fiber reinforced composites. Please.
To one and all. So I'll be talking about fiber reinforced ductile composite for seismic resistance building. So this will be the presentation outline. Introduction, technique to enhance ductility measurement, development of composite specimen, and results and discussion. So first of all, what is ductility? So it is the ability of a material to undergo large deformation, and it can also be measured elongation, strain up to the fracture point of any specimen, or simply the horizontal distance on the strain axis. So why ductile composites? So they have been already used in civil engineering application. For example, bridges, decks, pipelines, storage tanks, etc. But if you see in 2010, there is a big earthquake in Haiti which resulted to the death of about 1 lakh people. So many of them could not escape to the buildings also. So, and the country like India and Nepal are in the seismic zone with many old building monuments and transportation infrastructure that may not withstand such magnitude of earthquakes. So, which arises the need of such composites. So the application areas arise is very vast for composites. It is aeronautics, wind turbines, sports, civil and automobile also. So there are several techniques to enhance the ductilities. So discontinuous reinforcement architecture by introducing into the any polymeric material, then hybridization, fiber reorientation, and aligned discontinuous fiber reinforcement, stacking sequence, and the tactile matrix. So these techniques are basically able to produce different stress strain response or stress strain response with a plateau region, something like you can see in the blue curve, and the red curve shows the typical behavior of a brittle material. So they are less sensitive to the stress concentration, the ductile materials. So this is the example of design discontinuity. We can simply introduce some cut between the layers of the fibers to introduce it. Hybridization is basically introducing of lower failure strain fiber, are replaced with higher failure strain fibers. And then fiber orientation or ply orientation gives a more non-linear tensile stress strain curve and a more progressive failure behavior. And this is the technique to use high performance discontinuous fiber which is in aligned form, and you can see that percentage strain is increased if the fiber are aligned as compared to the random orientation. And then effect of stacking sequence. So low strain material, placement of low strain material in between high strain material shows the more progressive and more ductile behavior. And matrix of different ductility. You can see this is a comparison between epoxy and polyamide, and higher value of strain percentage is observed in polyamide matrix as compared to the epoxy matrix, which is brittle one. So ductility measurement, it is you can see from this curve the final failure strain difference between the final failure strain and the elastic strain at the same stress level on which we measure the initial modulus, and therefore the ductility in an inherently brittle material through control of damage mechanism is an intelligent choice for structural and mechanical parameters of composites. So these are the different ways to measure the ductility. The first curve is a typical stress strain curve for a steel specimen. So the distance between the ultimate stress and the fracture point could be a measure of ductility. And other is the comparison of by comparing the area under the curve of a tensile stress strain curve. You can see the blue curve is giving higher area under the curve, which means the higher energy absorptions, so the more ductile behavior. And the third curve is about the non-linear curve of different specimen. You see the bottom curve, which is towards the x-axis, is little non-linear compared to the other two. So the non-linearity is basically also indication of the ductile behavior. And the one which we focus here is the last one. Since composite are typically fail catastrophically, and it's a single fracture. So by introducing this design discontinuity, we try to achieve this multiple fracture failure so that we can get enhanced strain values, that is a measure of ductility. So this is the research gap which we talk. Basically, the composites are inherently brittle in nature, and they fail at a very low strain values. So although they have high strength, high stiffness, low density, and very good corrosion resistance. So we have developed some composite specimen using glass epoxy, epoxy as a matrix material and glass as a reinforcement. So this is a methodology we have followed for different techniques, and these are the results which we have achieved. You can see that when we have increased the number of cut in a single layer, so we have get the enhanced ductility, but up to 2 cut discontinuity. But as we have introduced the 3 cut in the same specimen, its strength and ductility both reduced. This could be due to the more basically resin-rich region due to the discontinuous portion of the fibers. And this is the effect of stacking sequence on ductility. You see, as the number of layer is increasing, your basically ductility is increased up to the 2 layer, and again on the 4th layer it has decreased because poor fiber orientation is normally achieved in thicker laminates. This is the comparison of failure strain. You can see the 2 layer give the highest failure strain, means the higher ductility, and the 3rd and 4th is also comparatively similar and better than the first layer 1. Now in the 3rd we have done the stacking of layer, and we have introduced the 2 cuts, only 2 cuts, but we have increased the stacking sequence. I mean 1 layer, 2 layer, 3 layer, number of cut is same. So in that also we have seen that as we increase the number of layers, you can see this behavior is changed from single fracture to the multiple fractures, and the ductility percentage also increased up to the layer 3, and in the layer 4th again it has reduced, but it is still higher than the layer 1 and the layer 2. Also we have seen the effect of fiber length on the ductility. So we have tried different fiber length, 1 centimeter, 2 centimeter reinforcement with 3 centimeter, and with increase in fiber length also the ductility percentage increased. This article we have published in Journal of Composite Material already, and so introducing cut within the UD layer into the failure strain increase up to 0.5%, and while stacking multiple layer combined with discontinuities, we have improved the strain up to 1.3%, and the highest gain we have achieved in the 3 layer cut composites. and the composite reinforced with the longer fiber, which is 3 centimeter. In case of chopped fiber reinforcement, we have achieved ductility enhancement of about 0.3%. And thank you so much. This is my Google Scholar.
If you have any question or discussion, please.
We have
and does fiber orientation have any effect on
fiber orientation study we have not done in this particular part. We are doing in the next part. Although aligned fibers gives the more ductile behavior than the random. It is already reported in the
Okay, thank you so much. So let's move to the next presentation, and this is the final one of this session. Our next presenter is Gurveer Singh from Maharaj Ranjit Singh Punjab Technical University, and title of his presentation is Artificial Intelligence in Fiber Reinforced Composites, a comprehensive review.
At MRSPTU, Maharaj Ranjit Singh Punjab Technical University. My today topic is Artificial Intelligence in Fiber Reinforcement Composite, a comprehensive review. As in my presentation overview is background and its motivation, artificial intelligence and machine learning taxonomy, composite designs and its optimization, microstructure property and its relationship, manufacturing process and its control, care monitoring and physics informed in neural networking, defects detecting in process quality manufacturing, mechanical property predictions, failure of and design prediction, structural health monitoring, multi-scale artificial modeling, autonomous manufacturing and sustainable composites and data challenges and federal learning, explainable artificial intelligence and challenges and its future directions. So first, background and motivation. Why composite can matter? Nearby 50% and it's more. It can used in aerospace, and 40% of composites materials are used in automotives, and in civil engineering 10 times it's used due to corrosion and resistance in steel, and 60% in marine. The challenge why traditional methods fail short: anisotropy and its heterogeneity, testing cost and time. For testing it takes time and it's very costly, and failure and its failure complexity. The failure chance in previous model, traditional models are very high, thereby we can use this composite material. In artificial intelligence and machine learning taxonomy composites, there are two methods, conventional and non-conventional, where conventional and unconventional, where we can use numbers of current, and in artificial intelligence and composite design optimization, where material selection, laminates, stacking optimization, and artificial neural networking and predictive surrogate, where design variables, analyzing method, performance outputs, and data transferring, train AI model with predictive surrogate and predicted performance of it. Microstructure and property relationship, where convolutional neural networking, microstructure analysis, microscopy images and predict material properties directly, detaching from fiber distribution, void contents, and in facial characteristics, where in inverse design with the gravitational analytic networking, where involves the design specially target properties of generates the optimal structure, shifts from trial and error to targeted material creation. Graph neural networking, where graph neural networking represents fiber network connectivity and geometry of graphs, enabling efficient multi-scale stimulation bridging microstructure to structure scale. Artificial intelligence in manufacturing and process control, process optimization, where machine learning models identifies optimal windows, autoclave, filament winding, real time for adaptive control, where QR monitoring is for neural networking integrate multi-sensor data to monitor QR state to real time, enable the adaptable QR cycle optimization. If we can talk about QR monitoring and physics informed neural networking, there are challenges of data security, computational demands, multi-physics coupling, non-linear behaviors, and multi-scale modeling complexity, where we can methodologies are traditional physics informed neural networking, theory constrained physics informed neural networking, and case-based, disjointed and hybrid, where these methods are used for the QR monitoring of that. Next is defect detaching. If we can talk about defect detaching, we can detect the defect with ultrasonic thermography and X-ray and CT scan, where we can ultrasonic can give the accuracy more than 95%, and its thermography gives 3 to 5 times faster report than others, and example X-ray can give the great explanation of the composite fibers. In process quality monitoring, machine vision systems, acoustic emission, machine learning, multi-sensor fusion, where machine properties predictions can random forest and extreme boost, long short-term memory, temporary damage evolution from loading history, failure life, and physics informed neural networking, where failure criteria better with less data. If we can talk about failure and damage prediction, defects, first ply failure from strain gauge arise to artificial sensors, classical failure mode type, model temporal sequence of damage states, trained on strain histories, crack provision, and estimates rule for current damage states, loading conditions, out performance, classify minor rules. We can talk about structure health monitoring, where damage detection and localization, deep learning on guided, where lamp wave data from piezoelectric sensor network achieves remarkable accuracy and for variable visible impact damage, and prognostic of assessment, where integrates history loading data and current damage state and environmental condition for forecast damage progresses. Multi-scale artificial intelligence modeling, where nano or micro fiber matrix interface properties, void nucleation, crystal structure of fibers, laminate ply orientation, thickness, interply failure, mechanisms and structural scales, where buckling, impact responsible fatigue life, multi-scale damage accumulation. If we can talk about autonomous manufacturing of sustainable composites, artificial intelligence or robots integrates, enables fully autonomous fabrication without human invention. Real-time agents learn optical automated fiber placement strategies through stimulation, then deploy in factory. If we can talk about sustainable and recycled composite, machine learning optimized fiber, natural fiber composite formulation like hemp, flax and jute for maximum performance with minimum environmental impact, predicts properties of recycled carbon fiber composites, enabling confident to recycled composite fiber, in structural application. If we can talk about the data challenges and federated learning, data security is the main. Composite testing is expensive, where failure data sets are by small necessity, often more than 1,000 specimens per condition, heterogeneous formats, priority sellers, bias and representatives. The solution of data security challenges are federal learning trains a shared global model assess to distribute data sets without sharing raw data. Each participant's data stays private only. Model granites are exchanged, fair data principles are exchanged where we can work on it properly. If we can talk about example artificial intelligence and trust and safety critical, thereby we can use the in aerospace and infrastructure artificial intelligence decision directly affects structural safety. Regulators, engineers and operators require understanding of why a model make a decision, not just it does. Challenges and future research detection. The current challenges are data quality and quantity and quality, interpermeability, computational cost, standardization. And the research priorities are multi-scale frameworks, open databases, uncertainty quantification and regulatory pathways. We can key conclusion, artificial intelligence is transforming the fiber reinforcement composite life cycle from design to end of the life. Artificial intelligence offers transformative capabilities across the entire composite value chain, 80% faster design, less than 95% defect detection, autonomous manufacturing, deep learning handles to multi-scale complexity and heterogeneity of composite in ways classified method cannot. Physics-informed neural networking represents the most promising prediction, combining domain knowledge with data-driven flexibility for reversed interpretability models. Key barriers remain data security, standardization, impermeability and regulatory certification for safety critical uses. Thank you.
Please. Okay, thank you so much. The organizing committee, they have prepared a certificate for the presenters. So I request Professor Mishra to join for presenting the certificate. Please. As a senior professor, please.
I will stand beside you.
Now I would like to invite Pavel sir to come forward and collect his certificate.
We'll stand beside you. You just stand. Please. Please come. Abhi, are you? Please. You are co-chair.
Okay, sir.
Now I would like to call Soumya Chaudhary sir for collecting his certificate.
One minute.
Now I would like to call Zunzaro Kamble sir for collecting his certificate.
एक तो दबा दिया था कोई
Now I would like to call Prikshit Paul sir for collecting his certificate. Sir, for collecting his certificate.
हाँ जी सर।
Now I would like to call Gurveer Singh sir for collecting his certificate.
हाँ जी सर।
Thank you all for joining this great session, and I request you all to join for the lunch, which is in the tennis
चार्जर मशीन में। हाँ जी सर, सामने आइए।
Thank you all.